In this lesson, we will look at the particle on a ring. The term particle on a ring refers to a particle that is confined to move on a circle of radius r at constant speed v. The velocity of the particle is not constant because even though its speed is constant, the direction of motion is always changing. The direction of the velocity vector is perpendicular to the radius vector, its displacement from the center. For example, if the particle is moving counterclockwise, then at this location, the vector is pointing in the direction shown here by the blue arrow. It is perpendicular to the radius vector, which is shown here by the green arrow. At this location, the velocity vector is pointing this way. Again, it is perpendicular to the radius vector. And at this location, the velocity vector is pointing this way. It is perpendicular to the radius vector. The magnitude of the acceleration can be shown to be v squared over r. Since v and r are constant, the magnitude of the acceleration, a, is also constant. The acceleration vector can also be shown to be always directed toward the center of the circle, regardless of where the particle is on the ring. For example, at this location, the acceleration vector can be represented by this green arrow pointing toward the center of the circle. And at this location, the acceleration vector can be represented by this arrow. Newton's second law says that force equals mass times acceleration. Or, in this case, the magnitude of the force is m times v squared over r, where m is the mass of the particle. Since m, v, and r are constants, we can say that the magnitude of the net force, that is causing the particle to follow the circular path, is also constant. The force and acceleration vectors point in the same direction. Thus, the Schrödinger equation for this system is an example of what is known as a central force problem. The force vector at any given location points toward the center of the circle. Looking ahead, we will find that solving the Schrödinger equation for this system will be useful for dealing with the Schrödinger equation for electronic motion in an atom, as well as the rotational motion of a diatomic molecule. For a particle moving on a circle at constant speed, its angular momentum, relative to the center of the circle, is also constant. The angular momentum vector, vector L, is the cross product of the radius vector r and the linear momentum vector p. The magnitude of a cross product is given by the magnitude of the first vector, in this case, vector r, times the magnitude of the second vector, in this case, vector p, times the sine of theta, where theta is the angle between the directions of the first and second vectors. Remember that the linear momentum is just mass times velocity. So, vector p points in the same direction as the velocity vector. For a particle moving on a circle, the velocity vector is always perpendicular to the radius vector. The angle between them is 90 degrees. Therefore, the angle between the radius and linear momentum vectors is also 90 degrees. So, for a particle moving on a circle at constant speed, the magnitude of the angular momentum vector is the magnitude of the radius vector, which is just the radius of the circle, times the magnitude of the momentum vector, which is just the mass m times the speed v, times sine of 90 degrees, which is equal to 1. Since m, v, and r are constants, the magnitude of the angular momentum is constant. What about the direction of the angular momentum vector? The direction of the cross product of two vectors is perpendicular to the plane of the two vectors. So, if vectors r and p are on the plane of this page, vector L would be perpendicular to this page. But would vector L be pointing toward you or away from you? Here's how to figure it out using the so-called right-hand rule. Hold out your right hand and point your index finger in the direction of the first vector. Turn your middle finger in, towards the direction of the second vector, and hold your thumb up. Your thumb should now be pointing toward the direction of the cross product. The directions of vectors r and p, as drawn on this page, would imply an angular momentum vector pointing toward you. In general, if you're looking at a page, counterclockwise motion on that page would mean an angular momentum pointing toward you. And clockwise motion would mean an angular momentum pointing away from you. Since the particle on a ring is moving at constant speed, its kinetic energy, T, is constant. And so is its potential energy, V. Obviously, the total energy, which is the sum of the kinetic and potential energy, is also constant. For convenience, we can take the potential energy as 0. Then, we can take the total energy as equal to the kinetic energy, which is equal to 1/2 mv squared, where m is the mass and v is the speed. It should be easy to show that it's also equal to p squared over 2m, where p is the linear momentum. And that it is also equal to L squared over 2m r squared, where L is the angular momentum, and r is the radius of the circle. The expression m times r squared is called the moment of inertia, and is typically represented by the uppercase I. So the total energy can also be written as L squared over 2I. Now, we're ready to look at how the particle on a ring is described in quantum mechanics. The time-independent Schrödinger equation is h hat psi equals E times psi. Here, h hat is the Hamiltonian operator. Lowercase psi is the spatial factor of a stationary state wave function, which depends only on the x and y coordinates of the particle if we choose our circle to be on the xy plane. And E is the energy corresponding to the stationary state. The Hamiltonian operator is just the sum of the kinetic energy operators for motion along the x and y axes if we chose the constant potential energy to be 0. We can greatly simplify the Schrödinger equation if we choose the center of the circle to be at the origin and replace the Cartesian coordinates, x and y, with polar coordinates, r and phi. R is the radius of the circle, and phi is the angle that the radius vector makes with the positive x-axis. From the diagram shown here, it is easy to see that x is equal to r times the cosine of phi, and y is equal to r times the sine of phi. Because the radius of the circle, r, is constant, doing this transformation of coordinates effectively reduces our problem from having two independent variables, x and y, to just one, phi. The expression for the Hamiltonian operator simplifies to negative h bar squared over 2I times the second derivative with respect to phi. Here, I is the moment of inertia, which is equal to the mass, times the square of the radius. The solution to the Schrödinger equation is relatively simple. The dependence of the wave functions on phi turns out to be given by n times e to the I times m sub L times phi. Here, m sub L is a quantum number that is restricted to integer values only. Please note that in some textbooks, the quantum number m sub L is also written as just m. When you see this, don't confuse it with the m that is also used as a symbol for mass. Where does the quantum number come from? It arises when we apply the condition that psi must be single-valued. Remember that on the circle, the location given by phi plus 2 pi is exactly the same location given by phi. So the value of psi must be the same at location phi and at location phi plus 2 pi. The normalization condition requires that the total probability of finding the particle on the circle is 1. This means that if we integrate the probability density function, psi star psi, or the square of the absolute value of psi, over all possible locations, we should get a value of 1. For a circle, all possible locations are covered by the interval phi equals 0 to phi equals 2 pi. It should be easy to show that the absolute value of the normalization constant n is equal to 1 over square root of 2 pi. What do the wave functions tell us about the probability of finding the particle on the circle? If we work it out, we find that all locations on the circle are equally probable. Here's how. Regardless of the quantum number m sub L, we can show that the probability density function is independent of location. It should be easy to show that the square of the absolute value of psi is equal to 1 over 2 pi. So what would be the probability of finding the particle within an arc from phi 1 to phi 2? Intuition tells us that if the probability density is uniform, we can just take the ratio of the length of the arc to the circumference of the circle. Indeed, if we integrate the probability density over phi, from phi 1 to phi 2, we get the ratio of phi 2 minus phi 1. 2 pi. Note that phi 2 minus phi 1 multiplied by r is just the length of the arc. And 2 pi multiplied by r is the circumference of the circle. If we take the ratio of the arc length to circumference, we get the same answer. Let's plot the wave function for m sub l equals 0. Plugging in 0 for m sub l in the expression for psi, we find that psi is equal to the normalization constant n, since e raised to the power 0 is just equal to 1. Psi is equal to a constant. In other words, psi is independent of location. Earlier, we saw that the absolute value of the normalization constant is 1 over square root of 2 pi. If we just use the absolute value of n for our normalization constant, then a plot of psi versus location would look like this. 1 over square root of 2 pi is about 0.4. We get a flat line at around 0.4. Here, location is shown on the horizontal axis in degrees. If you want to visualize this in terms of the circle, you can print out this graph, then roll the paper to superimpose 0 and 360 degrees. What about wave functions for non-zero m sub l's? Recall that both positive and negative integers are allowed values for m sub l. We can see that psi is complex. Remember that psi is equal to a normalization constant n times e to the power I times m sub l times phi. If we want to plot these functions, we need to plot the real and imaginary parts of the function separately. Using Euler's formula, we express the exponential term as a linear combination of sine and cosine function. The expression e to the power I times m sub l times phi is equal to cosine of m sub l times phi plus I times the sine of m sub l times phi. Taking the absolute value for the normalization constant, we can identify the real part of psi as n times cosine of m sub l times phi, and the imaginary part as n times the sine of m sub l times phi. Note that wave functions for states with the same absolute value of m sub l have the same real part since the cosine function is an even function. For example, cosine of negative 2 phi is equal to cosine of positive 2 phi. However, functions with the same absolute value of m sub l but with opposite algebraic signs differ in their imaginary part because the sine function is an odd function. For example, the sine of negative 2 phi is equal to the negative of the sine of positive 2 phi. Here's a plot of the real part of the wave functions for m sub l equals +2 and -2. The real part is 1 over square root of 2 pi times cosine of m sub l times phi. Whether we plug in positive 2 or negative 2 for m sub l, we get the same real part since cosine is an even function. We can see that the cosine 2 phi completes 2 cycles from phi equals 0 to 360 degrees. When phi goes from 0 to 180 degrees, one cycle is completed since the argument 2 phi goes from 0 to 360 degrees. The second cycle is completed from 180 to 360 degrees. The number of nodes, where the function changes algebraic sign, is 4. We can see nodes here, here, and here. In general, the number of cycles completed is equal to m sub l. And the number of nodes is 2 times m sub l. To visualize this graph in terms of the circle, print it out and roll up the paper into a circle so that 0 and 360 degrees are superimposed. Here's a plot of the imaginary parts of the wave functions for m sub l equals +2 and -2. The imaginary part is 1 over square root of 2 pi times sine of m sub l times phi. It matters if we plug in positive 2 or negative 2 for m sub l. We get positive 1 over square root of 2 pi times sine of 2 phi if m sub l is positive 2. And we get negative 1 over square root of 2 pi times sine of 2 phi if m sub l is negative 2. The plot for m sub l equals positive 2 is shown here as an orange curve. And the plot for m sub l equals negative 2 is shown here as a gray curve. We can see that sine 2 phi completes 2 cycles from phi equals 0 to 360 degrees. When phi goes from 0 to 180 degrees, one cycle is completed since the argument 2 phi goes from 0 to 360 degrees. The second cycle is completed from 180 to 360 degrees. The number of nodes, where the function changes algebraic sign, is 4. We can see nodes here, 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 and here. Note that the node at phi equals 0 is the same node at 360 degrees. 0 and 360 degrees refer to the same location on the circle. In general, the number of cycles completed is equal to m sub l. And the number of nodes is 2 times m sub l. To visualize this graph in terms of the circle, print it out and roll up the paper into a circle so that 0 and 360 degrees are superimposed. The energy for a quantum state associated with a given m sub l is m sub l squared times h bar squared over 2I. Here, I is the moment of inertia, which is equal to the mass of the particle, times the square of the radius of the circle. The expression h bar squared over 2I is called the rotational constant and is typically represented by uppercase B. Obviously, energy is quantized since m sub l values are restricted to integers. What would be the 4 lowest allowed energy levels in terms of B? Let's draw an energy level diagram. The ground state energy, or lowest allowed energy, corresponds to m sub l equal to 0. The energy is 0 squared times B, or 0. The first excited states correspond to m sub l equal to plus 1 and minus 1. The square of plus 1 or minus 1 is 1. So the first excited state energy is 1B. The second excited states correspond to m sub l equal to plus 2 and minus 2. The square of plus 2 or minus 2 is 4. So the second excited state energy is 4B. The third excited states correspond to m sub l equal to plus 3 and minus 3. The square of plus 3 or minus 3 is 9. So the third excited state energy is 9B. How would you describe the degeneracies of the allowed energy levels? We can see from the energy level diagram that all the energy levels are doubly degenerate except the ground state. We say that there are 2 ways that the particle can be in a given excited energy level. But the ground energy level is non-degenerate, or singly degenerate. Don't forget that the wave function does depend on both location and time. For stationary states with well-defined energy E, the wave function for the particle on a ring, represented here by uppercase psi, is a product of a function of location phi, represented here by lowercase psi, and a function of time, e to the negative I t over h bar. By solving the time-independent Schrödinger equation, we found little psi to be e to the I times m sub l times phi times some normalization constant n. And we found the energy to be m sub l squared times the rotational constant b. By multiplying the exponential terms, we get an exponential term from which we can easily see that the real part of psi is n times cosine of m sub l phi minus m sub l squared bt over h bar. And the imaginary part of psi is n times the sine of m sub l phi minus m sub l squared bt over h bar. Recall that for a stationary state, the probability density function, big psi star times big psi, is equal to little psi star times little psi, and should be independent of time. In this case, for any state associated with quantum number m sub l, the probability density turns out to be just the square of the absolute value of the normalization constant n. As we have seen earlier, this is equal to 1 over 2 pi. Shown below are the real and imaginary components of the stationary state wave function for a particle on a ring at time 0. The real component is shown in blue and the imaginary component is shown in orange. The horizontal axis spans 0 to 360 degrees. What do you think is the quantum number m sub l? Given the number of nodes shown, the quantum number m sub l is 1. Remember that the number of nodes in either real or imaginary component is 2 times m sub l. Now watch what happens as time advances. You can see that the value of the real and imaginary components oscillate at any given location. We have seen that for a particle on a ring, degenerate states have m sub L values that have the same magnitude. They only differ in algebraic sign. We have also seen that although their real components are the same, their imaginary components have opposite signs. This makes the wave functions linearly independent, which means that they must represent different physical states. But how are the physical states different? Let's look at an example. Let's compare the quantum states for m sub L equals +2 and m sub L equals -2. We have seen that they have the same energy. Remember that the energy is equal to m sub L squared times the rotational constant b. The square of +2 and the square of -2 are obviously the same. The probability density functions are also the same. As we have previously seen, it's independent of location and is equal to 1 over 2 pi. So how could they be different? They differ in their angular momentum. Recall that, classically, the angular momentum vector for a particle confined to a circle on the xy plane is pointing either in the positive z or the negative z direction. The quantum mechanical operator for the z component of the angular momentum, L sub z hat, can be shown to be h bar over I times the partial derivative with respect to phi. If we apply this operator on psi, we find that psi is an eigenfunction, with eigenvalue equal to m sub L times h bar. In other words, for quantum state with m sub L equal to +2, the z component of the angular momentum is well defined and equal to positive 2h bar. It's pointing in the positive z direction. For quantum state with m sub L equal to -2, the z component of the angular momentum is also well defined but is equal to negative 2h bar. It's pointing in the negative z direction. In terms of classical motion, a particle with positive L sub z is going counterclockwise around the circle on the xy plane. A negative L sub z means a clockwise motion. Do keep in mind that in quantum mechanics, we cannot talk about a definite trajectory. Before we move on, here's a quick review question about commuting operators and the uncertainty principle. Given that the complete set of eigenfunctions we obtained for the Hamiltonian operator are also eigenfunctions of the LZ operator, would you say that the Hamiltonian operator commutes with the LZ operator? Recall that if two Hermitian operators have a common complete set of eigenfunctions, then we can prove that they commute. Yes, the Hamiltonian and LZ operators commute. And we can see that it is possible to precisely measure both energy and the z component of the angular momentum at the same time. What happens when we take linear combinations of degenerate states? For example, suppose we take a linear combination of the wave functions for m sub L +2 and m sub L -2, with each having a coefficient of 1 over square root of 2? If we substitute the expressions for the wave functions associated with these quantum numbers, we find that we can simplify the expression to 1 over square root of pi times cosine of 2 phi. In general, if we take linear combinations with these coefficients, we'll find that the argument for the cosine function will be phi times the absolute value of the m sub L's. Do we expect the wave function to have a well-defined energy? The answer is yes. Since the wave functions for m sub L +2 and -2 are degenerate eigenfunctions of the Hamiltonian operator, any linear combination of the two wave functions will also be an eigenfunction with the same eigenvalue. In this case, the energy, the eigenvalue for the Hamiltonian operator, will be 4 times the rotational constant b. How about the z component of the angular momentum? We've seen that for m sub L +2, the eigenvalue for the LZ operator is positive 2h bar. And for m sub L -2, the eigenvalue is negative 2h bar. While the two functions are degenerate as far as the Hamiltonian operator is concerned, they are non-degenerate as far as the LZ operator is concerned. Since psi, in this case, is a linear combination of non-degenerate eigenfunctions of the LZ operator, it is not an eigenfunction of the LZ operator, which means that LZ is not well defined. We can calculate the expectation value of LZ. It will just be equal to 2h bar, the eigenvalue for m sub L +2, times the probability that a measurement of LZ would yield 2h bar, plus negative 2h bar, the eigenvalue for m sub L minus 2, times the probability that a measurement of Lz would yield negative 2h bar. The probabilities of obtaining the Lz eigenvalues are given by the square of the absolute values of the coefficients of the eigenfunctions in the linear combination. The coefficient of psi for m sub L plus 2 is 1 over square root of 2. So the probability of getting 2h bar if Lz is measured is the square of 1 over square root of 2, or 1/2. Similarly, the probability of getting negative 2h bar if Lz is measured is 1/2. There is a 50% chance the angular momentum vector is pointing upward with a magnitude of 2h bar, and a 50% chance it is pointing downward with a magnitude of 2h bar. The expectation value is 0. We just saw that taking a linear combination of wave functions for m sub L plus 2 and minus 2, with coefficients of 1 over square root of 2 for both, gives us 1 over square root of pi times cosine of 2 phi, which is also an eigenfunction of the Hamiltonian operator with the same eigenvalue. If we instead use 1 over I times square root of 2 and negative 1 over I square root of 2 as coefficients, we can get 1 over square root of pi times sine of 2 phi, which is also an eigenfunction of the Hamiltonian with the same eigenvalue. Since cosine 2 phi and sine 2 phi are linearly independent of each other, we can replace the wave functions with m sub L plus 2 and minus 2 by these two functions. We can do likewise for other degenerate pairs of m sub L's. But why would we want to do it? It just so happens that the cosine and sine functions do not have an imaginary component, so they would be easier for us to visualize. Note, however, that this new complete set of eigenfunctions for the Hamiltonian operator would no longer be a complete set of eigenfunctions of the Lz operator. Finally, please note that the probability density function will not be uniform around the circle anymore except for the ground state.